structure and breathing mechanism of fish. How does fish breathe?
Is open, the operculum slits are flush against the sides of the fish's body, meaning that the operculi are closed. In fish, water flows through the mouth, into the buccal cavity, and then over the gills and out underneath a flap called the operculum. This flap right here is the operculum. It's a protective covering that covers the gills to prevent damage. You can tell if a fish is ventilating by the fact that its operculum is flapping. We're now going to slice our fish open this way in order to look at what happens inside its body when it ventilates. Right now what we're looking at is a cross-section of the fish where the plane is parallel to the floor. On the left side of the screen you can see its mouth, and then on the top and bottom of your screen you can see its operculum. It has an operculum on both sides of its body, one on the left and one on the right, which protects the gill slits, which are right here. When the fish opens its mouth, water flows into the area called the buccal cavity. The fish needs to push the water over its gills and then out of the operculum in order to extract the oxygen and remove the carbon dioxide from its tissues. To do this, the fish first closes its mouth. When it does this, the water is pushed out of the operculum openings, over the gills, and back into the water. As the water moves over the gills on its way out of the operculum, the oxygen is extracted and moved into the fish's bloodstream, and carbon dioxide is removed. We'll take a closer look at this in 1 second. We're now going to zoom in on these structures here on either side of the fish, which are known collectively as the gills. In this picture, we can clearly see the structures we call gills, and we can also see the fish's operculum opened right here. Notice that there appear to be many layers of gills on this side of the fish. This supportive structure right here is called a gill arch, and attached to it are many fibers that collectively extract the gases from the water. The red structures attached to the gill arch are called gill filaments. If we look even more closely at each gill filament, we'll notice that there are tiny hairs on them called lamellae. The nature of the lamellae makes the gill filaments a little bit fluffy and greatly increases their surface area, just like the cluster of bubbles in the alveoli of the lungs increase the lung surface area. The more surface area you have, the easier it is to do gas exchange. We're now going to look even more closely at the lamellae in order to see how gas exchange occurs in fish. In order to understand how lamellae work, we need to understand a concept called countercurrent exchange. Here I've drawn two sections, one that represents the water and one that represents one of the tiny hairs on the gill filaments called the lamellae. Now notice that the membrane of the lamellae is very, very thin. This means that there is going to be a very short diffusion distance, just like there was in the lungs. The goal of the lamellae is to get oxygen to diffuse out of the water and into the fish. To do this, we have the water flowing in a different direction from the blood flow inside the gills. In order to keep the fish alive, diffusion of the oxygen must be occurring at all times. If it stops, the fish will suffocate. The blood that initially enters the gills from the back of the gills has relatively little oxygen in it. For the sake of argument, let's say it has about 60% oxygen. In order for the fish to survive, we need 100% oxygen in its blood, otherwise the fish's tissues will not get enough. The water that comes in through the fish's mouth is full of oxygen. It's 100% saturated. As it moves farther through the fish, it's going to lose oxygen, which will diffuse into the lamellae. The blood that comes into the lamellae from the fish is going to start off with very little oxygen, but will gradually pick up more and more as it moves past the end of the gill filament. When the blood begins to return to the rest of the fish, it has a very high oxygen concentration. The concentration of oxygen in the water runs in reverse. When the water initially enters the fish's mouth, it starts off with 100% saturation, and then gradually decreases as the oxygen is sucked into the blood inside of the fish. When it finally exits the fish, it's going to have less oxygen than when it began. Remember that things like to flow down concentration gradients, from areas where there is more of it to areas where there is less. Because there is always more oxygen in the water compared to the bloodstream, the oxygen is always going to flow into the lamellae rather than flowing the other way. No matter whether you're in this area of the lamellae or whether you're in this area, the amount of oxygen is always greater in the water than it is inside the blood vessels. Because of this, diffusion occurs constantly rather than coming to a halt. In order to really understand this, we're actually going to flip them around and see what would happen if we had concurrent exchange, where both the water and the blood flow went in the same direction. Now let's look at what would happen if both the water and the blood were flowing in the same direction. Again, since oxygen likes to diffuse down the concentration gradient, it would flow really nicely on this part of the blood vessel right here, where the concentration gradient is very big. However, it would slow down towards the middle and end of the blood vessels because the concentration gradient gets a lot smaller. Eventually, it would come to a complete stop when the concentration of oxygen in the blood and in the water are the same. When diffusion is no longer taking place, it causes lack of oxygen to happen to all of the fish's tissues, and the fish will die. So, in order to make sure that diffusion is constantly happening, we use a countercurrent exchange system, where the blood and the water flow in opposite directions.